All right, class has started. How is everybody? All right, I'm handing out the attendance sheet. How many of you noticed that I did not hand it out every time? So what do we call that when I just do it sometimes? It's a sampling, yeah. Hopefully it's random, statistical sampling. Hopefully I've done it representatively so that I get it enough that it represents the overall attendance of the class. But this is actually just an accident. It wasn't on purpose. I intended to bring it every time, but there were a couple times I forgot. So yes, this is another case where we have statistical sampling. Is everybody doing well in their semester-long project? All right. Does anybody remember the date that you guys present your first time? Very good. Now, it'll be a Tuesday and a Thursday. If none of you, says you want to go on that first Tuesday, I'm just going to assign you guys, we'll go alphabetically. You have to do on Tuesday and half on Thursday. And yes,
Do we have in our guidelines for that presentation? What should be sometimes?
5 minutes, 3 to 5 minutes, maybe 3 minutes with 2 minutes for questions. Say what data you've chosen and what you know about it already. And you should have loaded it already. You should have some samples of the data to show us. Show us this is part of it. Maybe it's the CSV, maybe it's JSON, maybe it's images, who knows, whatever it is. But show us some actual data. I want to see something, strings, floats, integers, images, sound files, whatever it is, something loaded onto your computer in a way that you can do things with it. And then I'll ask questions, and maybe other people in the class will ask questions. But it'll be real strict, 5 minutes, you stop, you go to the next student or person. And that's the only way we'll get through everybody. Any questions or thoughts about that? What are the other two you mentioned? You cannot use Excel because it's not programming. You need to choose language. And as for PowerPoint, the way you present, yes, you can present them in a PowerPoint slide or in Google Slides or something. But there needs to be all the coding that you do for this project will be done in an actual computer language, not Excel. Python is the easiest one, but you're welcome to choose R or Rust or C, C++, Perl, COBOL, if you want. But it has to be a real full computer language.
Do we have to make slides, or could we just show from the code?
That's fine too. You don't have to make slides.
Let's go.
In fact, some of you like VS Code. That's a good place to do your coding if you want, instead of a notebook. And VS Code, I think, has its own notebooks as well if you still like notebooks, but love VS Code for some reason. And you can just present things from your computer using whatever is easiest for you. And that could be the easiest thing to do is literally stand up here with your laptop, hold it and show it to me. That would be the fastest. If you want to connect up here, we can do that too, but that does take a little bit of time. And getting everybody's computer connected to the screen is going to be kind of a mess. So bring your laptop. The easiest way to do this is probably you'll stand here with your laptop, talk me through things, and then the next person come up, do the same. Does anybody have any suggestions for how that could go better? Or is that the best? Yeah. You can have a Google presentation, yes. I do not. There might be one. And I don't see one, but there might be one. And if you're willing to come in before that class and make sure it works, you're welcome to do it that way.
You say the presentation's more like personalized with you.
Your project. And if you're doing it with someone, you do it together.
Okay. But like if I'm like when I'm presenting it on the day, I would present more to you than that.
Yeah, I'll be the one doing it, but everybody's got to be able to hear you, so project your voice, and you might get a question from the audience. But it doesn't, I don't think we have time to put everyone up on the screen unless we have an HDMI cable that magically works wonderfully. That'd be great. But think more about presenting to me and the whole class is listening to.
If you create like a shared drive folder, like our presentations. Yes.
That's a good idea. That is possible too. And you guys are all welcome to do that. And if you want to, you can coordinate on Discord, in the Discord channel. You don't have to do that, but you're welcome to. All right, let's get out our notebooks. Okay. And we'll start here again by reloading this cell and getting the Anscombe data into our data variable. Here we'll set the colors again. Then this cell is a little different. Take a look at what I've changed. You can change yours accordingly. Anybody need more time? Oh, deactivate. And nothing else, just the word deactivate. All right. Then this is very similar to before, but now you should only have one color in there. Your X should only have one of those series. All right, everybody get that? Now we're going to learn how to find the line that best fits this. If I were to eyeball it, it might go like that. That's not a perfectly straight line, but imagine it was. What are the two things that define a line in 2 dimensions? What's that? Excellent. Well, why, usually we have y and x, and this is y equals something in terms of x. But there's 2 coefficients in that equation. If we usually write a line as y equals what? What's that? We're going to do a regression, but just think about the simple equation for a line. Yes, mx plus b. So what do we call b? The y-intercept. And m? Slope. The slope. So we have the slope and the intercept. We want to find the slope and the intercept for this blue line, theorizing that there is going to be a solution that is quote unquote best. Raise your hand if you think there's always one best solution. Raise your hand if you think there's sometimes more than one best solution. You're all wrong. In 2 dimensions, and I think possibly more dimensions, there's always exactly one best straight line through the data. Now, how do we define best? Anyone remember that 4-letter thing I keep saying?
It was you minimize the mean square something.
Yeah,
Mean square value.
mean squared error. And they often talk about it as taking the square root of that. So RMSE. So you take this, you square it, add it to the square of this, add it to the square of this, add it to the square of this. Turns out there is always a specific line that minimizes this, and it can be found explicitly with math. It is great, and we're going to find that now. This will take you a little longer to type in. Don't worry too much about what the NumPy array stuff is doing. It's just making the data into a format that linear regression likes. Linear regression is the process of coming up with this line, this perfect line. And we're just going to use the one inside of scikit-learn, also known as sklearn. And this is the kind of thing that you should copy and keep aside and use other times.
Was there a install this?
Yes, there might need to be. You might need to do pip install sklearn, but maybe you don't. Try it. I think with Google Colab, sklearn comes pre-installed.
Yeah, I was doing some yes.
Same thing with NumPy. NumPy is a set of math routines that are written in C, but we can use them from Python. This is how Python operates faster than it normally would. Here's the longer name for sklearn. If you have to pip and cell, sometimes it wants that.
Why do certain commands, like you have linear regression, why do they need a parentheses but don't have anything?
Yeah, that's Python wants every function to use parentheses. Every time you have a function call, and this is because sometimes you just want the pointer to the function. So let's say you have, some function, we'll call it some func. Let's say I define it, have all the stuff in here. Then later on, I wrote a really weird function that takes a function and runs it. So I have to be able to pass that function in as an argument, as what we call a first-class citizen. So I can call this other function and pass in some func as an argument. I'm passing a pointer to where that function is stored in memory. That's basically what's going on here. That's different from calling the function. When I call the function, I have to use the parentheses. Now, the thing up here has one extra level of complexity. So once you kind of store that away in your brain, let's look at this. What this thing is doing, we're importing this object. And what this is doing right here is calling it, is basically calling the constructor of that object. If you look in all Python objects, they start off with class something, and then under it you have def init for initialize. And you have the other code under here that says what to do when you initialize this object. But when you just directly call that object with parentheses, it's calling this def init. And when it finishes, it returns a pointer to that object. Not the object definition, but the instantiated version of the object. For instance, if you had an object teacher and you called it and you gave it a name, Graham, my name, and it returned, it would return a pointer to where the Graham teacher object is stored in memory. And that's what's going on right here. That calls this function, but remember the function is actually a constructor. And the weird thing is, before it returns, it's calling another function on that object. So yes, this gets to different levels of complexity, and you guys should learn what all these little steps mean. In this case here, this linear regression object, it is being created, instantiated because of the parentheses. Then, after it exists, you're doing a dot fit on that. And the dot fit method of that object is going to take the X and the Y that we were passing in, and it's going to fit it. That means it's going to find that line and do the math for us. And then what it returns is a pointer to that original object. We could do this in 2 lines instead. First of all, that's the output that we'll get from this. But if we did this in 2 lines, There. That does the same exact thing.
Oh. You have to put the array. The array of capital X.
So up above, we had created the list, capital X and capital Y.
That's being capitalized.
And then in here, yeah. We're creating X2 and Y2 just to keep them separate. And these are basically the same data, but instead of a Python list, it's a NumPy array. And the NumPy array is something that it's just an object in this class called NumPy. And remember, NumPy is just written in C, but accessible from Python. And it makes Python able to do math quickly, more quickly than it would. Did the error go away? All right. When you run it, you should get this. Who got an intercept of about 2.99? All right. And who got a slope of about 0.5? All right, for those of you who did not, I'd like to see if you have.
I forgot to include it.
Okay.
For instance.
Go ahead, Stan. Okay, you should let me see that part. Make it look like that.
Yes.
Are we in this row? Good. All right. You got the right slope and intercept. Thank you.
Well, I had an error. Okay, remember to change the top part, the red dots. Yes.
All good?
No, mine's not good. Oh, you're not doing that.
Oh.
Oh, you have X and X.
Oh.
All good here? All good? Oh. This part is not. That.
Yes. So,
Yeah.
So I got one.
So you gotta import this one. Yeah, make sure that you open the file, it's actually gonna be I think it's called like sample data dash inscom media JSON. You do for yeah. This is the okay, yeah, so you just, the one that you have to do is in the Google Colab. So, well, the one thing you. So you gotta go into the sample data. Yeah, and then. Yeah, so, oh yeah, so then you just go into sample data and just download the install data. So it should be in the 3 dots. Download these. How are you guys? Oh, I got the code. Yeah, it is showing. Good. Yes.
I don't know. I got.
Okay, any other questions? All right, the slope and the intercept should be the theoretical best line. And we will look at that again next time, maybe a little more detail. So don't get rid of that notebook. All right, getting back to the lecture materials. We have all these different kinds of, what are they called? Begins with a D. The binomial, what'd you say?
Distribution.
Yes, distribution, or the Poisson distribution, or the beta distribution. These all come from statistics and probability theory. And some of them are left skewed, some of them are right skewed. And when they're skewed, the mean and the median won't be the same. Remember the salaries or wealth in Bellevue, Washington. The average will be way higher than the median because 2 guys at the top are skewing the average for everybody. So the average is often not what you should look at. You should look at the median instead. Now, who can remember what variance tells us? Just intuitively. Yeah, how spread out the data is. If you actually calculate the variance, what you do is you take the mean, that's how they define it, not with the median, but with the mean, and you go to every value in your data. You subtract one from the other and you square it. That's what these numbers all are. This is, some data point minus the mean, then you square and add it to this, and add to this. And if there's 24 data points, we're gonna divide it by 23. That's odd, isn't it? Why wouldn't we divide by 24? What's that?
We're calculating the same variances, but on those variances.
That could be the deeper reason. There's something called bias that pops up. And the variance will be biased if we just use 24. So we just divide it by 24 minus 1. And this is something that comes out of statistics. And I don't remember the deeper reason why, but if you ever had to calculate variance, that's how you do it. And the standard deviation is just the square of that. But the idea is to measure just how spread out it is. Which one has higher variance, the blue or the red? Who thinks blue? Yeah, I'm guessing blue is higher variance. Because for almost every one of these, if they're points, almost every one of these points, minus the mean squared is going to be a lot. If you add all this up, that'll be a lot. Now, if it's a continuous distribution, then you have to do some kind of interval. But let's pretend these are points. There's a certain name for having two bumps in your distribution. Does this remind you of something we talked about last time? Pepsi? Remember? There is no perfect Pepsi. There are only perfect Pepsis, plural. How did I describe that before in the data? How did I draw it? You guys remember me drawing a bunch of dots? Like this? And there's two clusters. You can almost think of these as two clusters. We call this a bimodal distribution. So the blue is bimodal. You can think of this as one mode and this is another mode. And of course, there's multimodal distributions. And if you know that there's two, you can say, okay, I'm going to posit that the blue is made out of two distributions that are both normal. So you've got normal distribution 1 being added to normal distribution 2. And since both are present in your data, you don't know which points come from which, they add together to create the blue two-humped curve. And you can see that in 2 dimensions here. If I saw this and I were Howard Moskowitz trying to decide for Pepsi how much aspartame is put into Diet Pepsi, I would say you need to make 2 versions. One of them with this amount and one of them with this amount. Call them different things. People will be super happy about this one, super happy about this one. But if you did it right in the middle, how many people would be super happy? Hardly anybody, right? This is the kind of data that they saw that day. And this kind of thing comes up a lot. And if you plot it on, if you're doing spaghetti sauce, let's say, and you have one of these being, you know, spiciness, and the other one being, let's say, garlickiness. Maybe you have a cluster here and a cluster here. If I saw this data, I would say we need to make two products. One of them has this much spiciness and garlickiness, and one of them has this much. And make them easily differentiable and recognizable in the supermarket. You will get many loyal customers who will love it. Who has heard of deciles or deciles? There's also quartiles, we can divide things into 4, or quantiles, we can divide them into 5. These don't look even for some reason. Some of them are thinner than others. Why?
Since they go further out, they actually have the equal amount, it's just distributed differently in that area.
Exactly. They presumably have the same volume or the same area. And if you're talking about points, actual data samples, they would have the same number of samples. There would be the 10% samples near the top, and 10%, the next 10% from, you know, 80% to 90, and from 70 to 80, etc. But this is a very typical way to think about any group of people or events or whatever. And it's a little bit like thinking about the median instead of the mean. Instead of, you know, averaging things, we'll say, you know, top 10% of, you know, people living in Bellevue, let's say. You look at them, and then the next, and the next, and the next. That's another good way to analyze your data. And this is the slide we ended with last time. When things are balanced, there's no skew, the mean and the median are the same. Otherwise, negative skew and positive skew will give that split. Okay, and this is something from your text and just shows if you split things into quantiles, sometimes the mean is a little bit outside of one of the quantiles. So you would expect it to be right in the middle, but it's not. For the same reasons. Now there's this z-score at the bottom. Has any of you heard of this thing? All right. Where you can get a z-score. The z-score right here is for one specific sample. So the mean here is 62.6. So what this does is it tells you something about that sample, how far from the mean it is. But if you're talking about data that's, let's say, in terms of, this is in travel time in minutes, we want a number that tells us how rare something is. And we don't really want that number to be in terms of minutes or in terms of feet or lumens or pounds. When a data point comes to us, we want to know if it's an outlier. Is this weird or is it totally normal? And the z-score can tell us that. Now, the mean is 62 here. And if we had a number that was around this area, it would be very normal, so to speak. This 30 is way below average. But how much below? If you just tell me, you know, 5 minutes below, that doesn't really tell me if that's weird or not. Like travel time, It's actually 32.6 minutes or. Yeah, 32.6 minutes below the average. And that may be a big deal if you're walking to work, but let's say it's a flight from, New York to Sydney, Australia. 32 minutes is not a big deal. So sometimes it's a big deal, sometimes it's not. If we want to know how much of a big deal it is, we look at all of the travel times together. And then we're going to divide by the standard deviation, which is just the square root of the variance. Standard deviation, variance, think about them as being similar things. They measure the same thing. They measure how spread out the data is. So if you have really long travel times, like let's say it's a cross-country drive, that takes most people a few days. Some people take a week. I actually did it once in 2 weeks, and it was wonderful. Taking your time, driving all the way across the country. My dad and I drove from North Carolina all the way back here to Washington State during the pandemic. Great father-son time. One of my favorite memories. We took 2 weeks to do it. We actually planned for 1 week, but then we hit a deer in Nebraska. Had to spend an extra week in Nebraska. So if we had been 30 minutes, if we'd gotten there 30 minutes ahead of time and the trip was, a week minus 30 minutes instead of a week, that's not an outlier. You need to put all the travel times up, see what the standard deviation is, and divide your difference from the mean by that standard deviation. And that gives you a number. And there is something called a standard deviation, which means one standard deviation, or standard deviation equal to 1. But we are 1.26 standard deviations below the mean. This is how we intuitively judge each single sample. Kurtosis. Sometimes this feels like vocabulary section of class, right? It's just vocabulary, more words. We got variance, we got standard deviation, we got distribution, we got gamma distribution, beta, we got kurtosis now. Kurtosis, pointiness. That's how I think about it. Pointiness. It also sounds like a disease that your distribution might get. Came down with a case of kurtosis. So the more pointy it is, the more kurtosis or more kurtotic the curve is. Oh, it's so kurtotic. Ouch, that hurt. All right. How much are you gonna win if you play this game? Of course, if it lands on the $2, like in that example there, you win $2. But what are you probably gonna win? What do we call that number that you're probably going to win? The number you would expect to win. What's that? The probability? That's a term we like to use is expected value. The expected value of your win. It comes from probability theory. So on each slice of the pie, there's a different prize amount. But each slice of the pie seems to be the same size, right? So let's say same probability for getting any slice in this pie. We're going to assume that the wheel is fair and it's not trying to trick us in any way. So the expected value is just, if you think of it as the average winnings you would get if you played infinite number of games. How do we calculate that? Mean of each one of them, yeah. And if they had different probabilities, you would have to adjust for that. We did that, yeah. The probability space or sample space is something to think about here. We have exactly 8 choices. And those 8 slices is our entire space. You have a 1 in 8 chance of getting every one of those, but it's all the same. But that expected value is an important number to think about, and that would determine how much you would pay if you had to pay to play this game, right? Would any of you ever pay $100 to play this game? That'd be stupid, right? How about $50? Why would that be stupid? You might lose money, but you might win money. Why is $50 the wrong amount to pay to play this game? Yeah. There's only, well, there's 2 places. Actually, that's 50 cents, not $50. So yeah, only one time. How about $10? Is that too much to charge someone to play this game? Why?
You only win money once, you'll come out and win once, other times will be free.
Yeah. So you win at least $10 and only 2 slots. You think $5 is the right amount? All right, well, I'm going to show you a harder problem that seems simpler. Instead of 8 choices, it's just a coin. Head or tails, right? My question for each one of you is, how much would you be willing to play this game? Let's unpack that reward. Reward is equal to 2 to the n dollars. And you're being rewarded by the number of heads in a row. So if the first time you flip the coin, you get tails, that means you get 2 to the $0. That means $1. So you get something even if you fail the first time. You get $1. If you get 1 head, and then the next one is tails, and then you're out, then you get $2. So you're guaranteed to get at least $1. But you can get $2, or you can get $4, or 8, or 16, or 32, 64, 128, 256, 512, 1,024, 2,048. You might get $2,048, and in like 5 minutes, 1 minute will work. That's not bad, How much would you be willing to pay? Let's hear some numbers.
It's just $2.
You're $2. Who's go higher? What do you pay? All of your money. Good answer.
No.
Good answer. What else? Who would? We don't know how much money you have, but who would go higher than all? Who would actually agree with them? All your money. Okay, let's estimate the expected value of this variable. Reward here, we're calling it a Random variable is just something we use in statistics, the term random variable. It's something you don't know what it's going to be, but then you find out. Okay, so the expected value of the reward, BR, is going to equal the probability of one head or 0 heads times $1 plus the probability of 1 head times $2 plus the probability of 2 heads times $4. So what is this first probability? Probability of getting tails on the first try? 0.5. What's the probability of getting 1 head? 0.5 again, right?
Yeah,
Well,
details on this.
If you're getting, this is actually that first try still. Probability of getting 1 head. Maybe we should just start there.
Well, because you're.
Because here you got 0. This probably 1 and probably 0 has to add up to 1. So let's just start here, 0.5. Probability of getting 1 heads 1 time. That means you're getting on your first try. Probability that the first coin you flip is going to be heads is 0.5.
Well, so the way I would interpret this, if we were to actually like draw out a tree diagram for this, is that to get 0 heads, you would have to get a tail on the first one, which would be a 0.5 chance. And
Yep.
to get only 1 head, you would have to get a head followed by a tail.
Oh, that's a
So
good way
that
to
would
put
be
it.
0.25, and then you would follow that.
That sounds good.
Yeah.
Let's do 0.5 plus 0.25 times 2, which makes this, we'll do that in a second. Plus, this one is going to be 0.125, and then 0.0625. That you'll get 3 heads and then a tail. That was a good way to break that down. I like that. So this one we multiply by 2, this one we multiply by 4, this one we multiply it by 8. And what we get, and it goes on forever, right? So we get is 0.5 plus 0.5 plus 0.5 on and on forever. So the expected value is infinite. So that is the mathematically supported answer. You should bet all your money. This problem was so hard that I think Pascal had a really hard time with this probabilistic problem. And what they decided was that no one actually is going to give all their money for this because you're probably going to lose it. But there is an amount that's right for you. This is the first problem in probability, I think, that people came up with the fact that it depends on the player. It is not actually best for every player to play this game for the same value. You have to bet an amount that you're willing to just lose and walk away from. For some people, maybe that's $10. For other people, maybe it's much more. When you see a penny on the ground, do you bend down to pick it up? I don't, because it's not worth my time. If I see a quarter, I might not do it. Now, a lot of people would see a quarter, and it is worth their time to go down and pick a quarter. But someone calculated for Bill Gates how much there has to be on the ground for him to bend down and pick it up. Can anyone guess what that number is? $45,000. If Bill Gates is walking along the street and he sees $44,000, it's not worth his time to bend down and pick it up. So it would certainly be worth his $45,000 to play this game. Anyway, this is a funny divergence into expected value. And just remember that expected value is only part of the story. All right, in your text, you will see this page talking about sample space. Let's say that these 6 states or these 6 things are the things that can be chosen. And I'm going to give you one feature, and we have to look at the probability of some other feature. So if I tell you that given that the thing is mid-level, what is the probability that it's open? Given that it is mid, what's the probability that it's open? 50%. Yep, 0.5, we say. Given that it's low, what is the probability that it's open? Yep.
Would be this.
No, because all of the lows are open. So given that it's low, the probability is 1 that it's open. Given that it's high, what is the probability that it's open? What do you think? Yep. Makes sense, everybody? All right. Now, if we have the set of all things that are covered, these are actually people, and covered refers to health insurance. And the region is just where they live. So let's say we have the set of all people who are covered and the set of all people that live in the Northeast. Then we can start to look at certain things. Like, what is the probability that someone is in set A? Well, we have that. You just computed. Probability that someone is in set B. What is the probability that someone is in A and B? And then that is different from this. Who knows how you say this? Yeah. So if you have someone who is in set B, what is the probability they're also in set A? And that comes out to be a very different number from probability of A and B. You can also put it on a tree. There's this old question that they give to people in probability classes to talk about if you get a certain test for a rare disease, should you be worried? Well, here we have probability, the top there, B positive test and not B negative test. So B is this condition of having a disease. And I think the text is talking about cystic fibrosis. So some of the people who have cystic fibrosis, when they take the test, they get a positive test. Some of them have a negative test. Some of the people who do not have cystic fibrosis have a positive test. It's not saying that though. Not A, just that. Okay, A is the ones who have cystic fibrosis. So if you look at entire population, the number of people that half cystic fibrosis is very small. So the probability that you have it is 0.0003. But that's different than your probability of getting a positive test. And when you look at the positive tests, so out of the people who don't have it, 0.0018 of them, which is not many, they will have a positive test. If you have a positive test, you can hope that it was given to you as a mistake. That feels like a very small chance. Like if they tell you that out of the people who don't have it, hardly any of them, 0.0018 of them, they have a positive test. But why should you still not feel too worried?
Because the chance of having it in the first place is so.
Yeah, meaning, look how many people come down this branch, 0.9997. And people that have it, it's so small. Even though this percentage is tiny, it's a tiny percentage of a huge population. Whereas the other way, if you do have it, there's actually a pretty good chance you're going to get a negative test, which is not great. Like a 12.5% chance you will get a negative test, even if you have it. So it's not a perfect test. No tests are perfect. This relation up here, have any of you seen that?
Yes.
What is it called? Bayes' rule. So Bayes' rule. It's a way to get the probability of one set given another in terms of that other set given this set. Let's pretend you want to know the probability of A given B, but you don't have that number, but someone was able to give you the probability of B given A. So Bayes was the first guy who came up with this relationship. Probability of B given A times the probability of A over the probability of B equals this, probability of A given B. And I want to show you where that comes from, a way you can easily derive this yourself if you ever forgot it. So in this diagram here, which section represents the probability of A given B? I mean, what sections, how would you graphically think of it?
Maybe the portion of circle B that lies in the intersection.
Over,
Oh, well, that would, I mean, so it would be the intersection divided by the total.
yes,
Set B.
yeah, so given B means that you're already inside the B circle somewhere. Inside that B circle, what is the probability that you're also in A? It's that intersection, right? But it's not just the intersection, it's the intersection over the entire B circle, right? Then how do we describe the probability of B given A? What do you think? Who knows?
Probably the intersection. Just the A circle.
Yeah, the probability, you would take the area of this intersection and divide it by the area of all of A. That gives you the probability of B given A. Because think about it. Given A means you're in A somewhere. And how much of A is also in B? It's that intersection. Well, let's do a little math. We begin with the intersection, right? Okay, the intersection equals itself. Duh. Well, we can multiply and divide something by the same thing without changing its value, right? So let's do that. We're gonna choose A. Now I made it smaller just so it all fits, but pretend it's still big, okay? I'm gonna take the right side of the equation, I'm going to divide it and multiply it by the same value. Doesn't change the value. Now I'm going to divide both sides by b. I can do that. It's an equation. And b isn't 0. Assuming b isn't 0. Now I just shifted around a little bit. And this, the intersection overall of b, is probability of a given b. And then up there, I have the probability of b given a times probability of a over the probability of b. And there's Bayes' rule. Bayes' rule is so important. There's Bayesian everything. There's Bayesian nets, Bayesian learning, Bayesian statistic. There's all kinds of people love Bayes. And I think that's a good place to end today. If you have any questions, come find me.
For Bayes' rule,